Picture this. A sudden flare of energy brighter than 1,000,000 suns erupts in the darkness of space. A violent cosmic dance where magnetic fields collide, snap, and rearrange in an instant. This isn't science fiction. It's magnetic reconnection, one of the universe's most explosive and mysterious phenomena. Scientists have witnessed it on the Sun, in Earth's magnetosphere, even in distant galaxies. But what if these violent events aren't just cosmic accidents? What if there's something far more extraordinary, hidden gateways, cracks in the fabric of reality itself, leading to realms beyond our own? For decades, physicists have been piecing together the puzzle of magnetic reconnection. It's the invisible force behind solar flares, auroras, and even disruptions to our power grids. But beneath the textbook explanations lies a tantalizing secret. When magnetic fields break and reconnect, they release unimaginable energy so intense it warps space and time. Could these fleeting moments of chaos be the key to unlocking doors to parallel dimensions? The idea sounds like something from a fantastical tale, but cutting-edge theories in quantum physics and cosmology suggest there might be truth hidden in the chaos. Imagine a universe where every burst of magnetic energy isn't just a natural event but a fleeting doorway, a chance to step into the unknown. This is where science edges into the realm of the extraordinary. Think of space as a vast ocean and magnetic reconnection as the whirlpools that form where currents clash. Most whirlpools vanish without a trace, but what if some of them lead somewhere deeper? What if, just for a fraction of a second, they open passages to worlds where the laws of physics bend differently, where time flows backward, or where alternate versions of reality exist? Today, we're diving into the heart of this cosmic mystery, exploring the groundbreaking research that's turning science fiction into plausible science. From laboratory experiments to observations of distant galaxies, the evidence is mounting that magnetic reconnection might be more than we ever imagined. So buckle up, we're about to journey to the edge of known physics, where the universe's best-kept secrets might be hiding in plain sight. Magnetic reconnection sounds like something out of a high-energy physics lab, but it's actually happening all around us and even inside us. Every time your heart beats, tiny electrical currents generate magnetic fields. On a cosmic scale, the same basic process unfolds with unimaginable force. Picture two gigantic magnetic fields stretched like rubber bands pressing against each other in space. The tension builds until, snap, the fields break apart and suddenly reconnect in a new configuration. That sudden release of energy is magnetic reconnection, and it's one of the most efficient ways the universe converts stored magnetic energy into heat, light, and explosive motion. Take the Sun, for example. Those beautiful loops of plasma arching from its surface are shaped by magnetic fields. When these fields twist too tightly, they snap like overstretched cables, triggering a solar flare. In mere seconds, these flares unleash energy equivalent to billions of atomic bombs. Closer to home, Earth's magnetosphere, our planet's magnetic shield, constantly battles the solar wind, a stream of charged particles from the Sun. When the solar wind's magnetic field clashes with Earth's, reconnection occurs, funneling energy into our atmosphere and sparking the shimmering auroras near the poles. Without this process, those dazzling lights wouldn't exist. But here's what really baffles scientists. Magnetic reconnection happens far faster than classical physics predicts. In theory, the resistive forces in plasma should slow reconnection down to a crawl. Yet in reality, it occurs almost instantly, like a zipper being ripped open. Laboratory experiments, like those in magnetic confinement fusion reactors, have shown that tiny instabilities, chaotic swirls in the plasma, can accelerate the process exponentially. This mismatch between theory and observation is why reconnection remains one of the biggest unsolved puzzles in plasma physics. What makes it even more fascinating is its scale-invariant nature. Whether it's a small eruption in a lab or a galaxy-spanning jet powered by a supermassive black hole, the same fundamental process repeats. That universality hints at something deeper. Magnetic reconnection might be a cosmic signature, a fundamental mechanism woven into the fabric of space-time itself. Scientists suspect it could even play a role in phenomena we don't fully understand yet, like fast radio bursts or the mysterious heating of the sun's corona. So why does this matter beyond satisfying scientific curiosity? Understanding reconnection could revolutionize technology, from protecting satellites from solar storms to unlocking the secrets of stable nuclear fusion. But perhaps the most tantalizing possibility is that these violent magnetic rearrangements aren't just energy releases. They might be transient windows into the underlying structure of reality, where the very rules of physics get rewritten in fleeting bursts of chaos. And that's a mystery worth chasing. The story of magnetic reconnection begins not in the vast emptiness of space, but in the quiet halls of mid-20th century laboratories. It was Swedish scientist Hans Alfvén who first proposed the radical idea that magnetic fields in plasma could break apart and reconnect, a theory so controversial at the time that many of his peers dismissed it entirely. Alfvén, who would later win the Nobel Prize for his pioneering work in plasma physics, saw what others couldn't: that the universe wasn't just filled with static magnetic fields, but with dynamic, snapping lines of force capable of explosive transformations. His insights laid the groundwork for understanding everything from solar storms to the northern lights, though it would take decades for technology to catch up with his vision. The first real evidence came from early space missions in the 1960s and 70s, when satellites began detecting strange bursts of energy in Earth's magnetosphere. Scientists noticed that during geomagnetic storms, charged particles weren't just drifting along magnetic field lines, they were being violently accelerated, as if shot from a cosmic slingshot. These observations matched Alfvén's predictions perfectly, proving that magnetic reconnection wasn't just theoretical, it was happening right over our heads. By the 1980s, advanced computer simulations finally revealed how the process worked. Opposing magnetic fields would draw closer, thin out, and then, like a rubber band stretched too far, suddenly snap into a new configuration, releasing pent-up energy in an instant. But the real game-changer came in 2015, when NASA launched the Magnetospheric Multiscale Mission, or MMS. This fleet of 4 identical spacecraft flew in a tight pyramid formation, carefully positioned to study reconnection events at unprecedented resolution. What they found stunned researchers. Instead of the slow, steady process predicted by earlier models, MMS witnessed magnetic fields breaking and reconnecting in chaotic bursts, with particles accelerating to nearly the speed of light in mere seconds. The mission's data revealed whirlpool-like structures in the plasma, tiny vortices that acted as cosmic accelerators, solving part of the mystery behind reconnection's startling speed. These discoveries didn't just happen in space. Back on Earth, teams working with experimental fusion reactors faced their own reconnection puzzles. In devices like tokamaks, where superheated plasma is confined by powerful magnets, unwanted reconnection events could suddenly destabilize the entire system, halting fusion reactions in their tracks. By studying these laboratory-scale explosions, scientists realized that the same fundamental physics governed reconnection everywhere, from the small-scale experiments in their labs to the massive flares erupting on the sun. Today, we stand at the edge of a new era in understanding this phenomenon. Modern telescopes catch reconnection powering jets from distant black holes, while advanced probes examine its effects in Earth's protective magnetic bubble. Each discovery peels back another layer of the mystery, revealing a universe far more dynamic and interconnected than we ever imagined. And as we continue to study these cosmic snapshots, one question lingers: what else might magnetic reconnection be hiding? The Sun is a cosmic powerhouse of magnetic energy, and nowhere is that more evident than in the violent eruptions we call solar flares. These aren't just spectacular light shows, they're the result of magnetic reconnection on an unimaginable scale. Picture the sun's surface where loops of plasma, guided by magnetic fields, arc hundreds of thousands of kilometers into space. When these fields become twisted and strained, they reach a breaking point. In a fraction of a second, they snap and reconnect, releasing enough energy to power entire civilizations for centuries. The temperatures in these explosions soar to tens of millions of degrees, and the radiation they emit spans the entire electromagnetic spectrum, from radio waves to gamma rays. But solar flares are just the beginning. Sometimes reconnection triggers an even more massive event, a coronal mass ejection or Scie. These are billion-ton clouds of magnetized plasma hurled into space at speeds exceeding 1 million miles per hour. When a Scie heads toward Earth, it doesn't just deliver a light show, it has real-world consequences. In 1989, a powerful Scie caused a geomagnetic storm so intense it knocked out power across Quebec for 9 hours, leaving millions in the dark. In 2003, the infamous Halloween storms disrupted satellite communications, GPS systems, and even forced airlines to reroute flights to avoid radiation exposure. These events remind us that the sun isn't just a distant star, it's an active player in our technological lives. What makes these eruptions so unpredictable is the chaotic nature of magnetic reconnection itself. Unlike controlled laboratory experiments, the sun's plasma is turbulent and filled with instabilities that amplify the process. Scientists have observed strange phenomena like magnetic islands, tiny, self-contained loops of magnetic field that form and vanish within the chaos, accelerating particles to near light speeds. Satellite missions like NASA's Solar Dynamics Observatory and the Parker Solar Probe have captured stunning details of these events, revealing structures that resemble cosmic whirlpools, where magnetic fields twist, merge, and explosively release energy. The implications stretch far beyond our planet. Reconnection-driven eruptions on stars throughout the galaxy could influence the habitability of distant worlds, stripping atmospheres or bombarding planets with lethal radiation. Even black holes and neutron stars, the universe's most extreme objects, show signs of reconnection in their powerful jets. This suggests that the same fundamental process, fields breaking and reconnecting, might be a universal mechanism for energy release, operating everywhere from our backyard star to the farthest reaches of the cosmos. Understanding solar reconnection isn't just about protecting our technology, it's about deciphering a universal language of magnetic energy, one that shapes the behavior of every star, galaxy, and possibly even the hidden dimensions we've yet to explore. Each solar flare is more than an explosion, it's a cosmic clue waiting to be decoded. Earth's magnetosphere isn't just a passive shield, it's a dynamic battlefield where invisible forces clash in a spectacular display of cosmic physics. Every second, charged particles from the solar wind slam into our planet's magnetic field at speeds exceeding 1 million miles per hour. Most of these particles deflect harmlessly into space, but where Earth's magnetic field meets the sun's, something extraordinary happens. The opposing fields press together, stretch thin, and then like a rubber band snapping, they rupture and reconnect. This explosive moment, lasting mere seconds, unleashes a torrent of energy that funnels particles down toward our poles, igniting the sky with the shimmering glow of auroras. These dazzling light shows are more than just nature's fireworks, they're visible proof of magnetic reconnection in action. The process begins far above us in a region called the magnetotail, where Earth's magnetic field stretches like a windsock in the solar wind. When conditions align, reconnection triggers a sudden collapse of this elongated structure, firing jets of plasma toward Earth at breakneck speeds. As these particles spiral along magnetic field lines and collide with oxygen and nitrogen in the upper atmosphere, they release bursts of colored light, green, red, even purple, painting the night sky in otherworldly hues. But reconnection isn't always so benign. During intense solar storms, the energy dumped into our magnetosphere can trigger violent geomagnetic disturbances. In 2003, a series of solar eruptions caused reconnection events so powerful they compressed Earth's magnetic field on the dayside, generating induced currents strong enough to overheat transformers and threaten power grids across North America. Satellites in low Earth orbit faced a different danger: radiation belts swollen with high-energy particles, capable of frying electronics or piercing through spacecraft shielding. Astronauts on the International Space Station had to take shelter in more heavily shielded modules, waiting out the storm's worst effects. This is where space weather forecasting becomes critical. By monitoring the sun's activity and modeling reconnection processes, scientists can predict when and where a geomagnetic storm might strike. Agencies like NOAA's Space Weather Prediction Center track solar flares and coronal mass ejections, giving satellite operators and power grid managers precious hours, sometimes days, to prepare. When a storm is imminent, satellites can be put into safe mode, and power grids can adjust operations to minimize damage. Even airlines, which rely on high-frequency radio communications over polar routes, reroute flights to reduce radiation exposure for passengers and crew. The stakes are rising as our reliance on space-based technology grows. Modern GPS systems, global communications networks, and even banking transactions depend on satellites vulnerable to space weather. A repeat of the Carrington event, the colossal solar storm of 1859, could today cause trillions in damage and take years to recover from. Understanding magnetic reconnection isn't just about solving a physics puzzle, it's about safeguarding the infrastructure that keeps our world running. Yet amidst these practical concerns lies a deeper mystery. Some researchers speculate that reconnection might not be limited to our solar system, that similar processes could shape exoplanetary magnetospheres, influencing the habitability of distant worlds. Imagine a planet orbiting a turbulent star, its auroras 1,000 times brighter than ours, its magnetic field constantly reshaped by violent reconnection. Could these conditions foster life or sterilize a world before it even has a chance? As we peer deeper into the cosmos, the answers may lie hidden in the invisible snap and twist of magnetic fields, a universal language written in energy, chaos, and light. In controlled labs around the world, scientists are recreating the violent cosmic dance of magnetic reconnection. But instead of vast stellar explosions, they're working with plasma-filled devices no larger than a room. These experiments might seem small compared to solar flares, but they hold the key to unlocking one of the universe's most chaotic processes. Take the magnetic reconnection experiment at Princeton, where researchers fired 2 rings of magnetized plasma at each other at nearly 500,000 miles per hour. When the rings collide, their magnetic fields stretch, snap, and reconnect in a miniature version of the same explosions that power auroras and solar storms. What makes these lab experiments so groundbreaking is their ability to capture details no spacecraft can see. High-speed cameras and precision sensors record every microsecond of the process, revealing bizarre structures like plasmoids, self-contained bubbles of magnetic energy that form and vanish within the chaos. These fleeting structures act like cosmic particle accelerators, explaining why reconnection dumps energy so much faster than traditional models predict. But replicating space conditions on Earth comes with enormous challenges. Lab plasmas are denser and cooler than their cosmic counterparts, and containing them requires powerful magnetic fields that can destabilize at the slightest imbalance. One of the biggest surprises came from experiments with the Swarthmore spheromac, where scientists observed reconnection triggering spontaneous turbulence, a cascade of whirlpool-like eddies that supercharged the energy release. This discovery mirrored data from NASA's MMS mission, proving that the same physics governs reconnection whether it happens in a lab or across a galaxy. Yet even with these advances, mysteries remain. In space, reconnection often occurs in almost collisionless plasmas where particles rarely bump into each other, a state nearly impossible to recreate on Earth without massive, specialized facilities like the National Spherical Torus experiment. The stakes of these experiments go far beyond pure science. Understanding reconnection could revolutionize fusion energy research, where uncontrolled magnetic snapbacks halt reactions in devices like tokamaks. By studying how to suppress or harness these events, scientists inch closer to the dream of clean, limitless power. Meanwhile, defense agencies probe reconnection's role in high-energy plasma weapons, and astrophysicists use lab data to interpret telescope observations of distant supernova and black hole jets. Perhaps most tantalizing are the indirect clues these experiments offer about reconnection's potential stranger effects. Some theorists speculate that under extreme conditions like those near neutron stars, magnetic reconnection might briefly warp spacetime itself, creating conditions akin to microscopic wormholes. While that remains speculative, lab results keep pushing the boundaries of what we thought possible. Each time scientists tweak the parameters adjusting plasma density, magnetic field strength, or collision angles, they uncover new layers of complexity in this deceptively simple cosmic phenomenon. And with every breakthrough, the line between controlled experiment and cosmic revelation blurs just a little more. The way magnetic fields snap and reconnect has puzzled scientists for decades, and to unravel this cosmic riddle, they've developed competing theories, each offering a different lens on why reconnection happens so explosively. The earliest and simplest of these is the Sweet-Parker model proposed in the 1950s. Picture two massive magnetic fields pushing against each other like tectonic plates. According to this theory, the fields slowly squeeze plasma out of the way, forming an elongated, narrow region where they eventually reconnect. But there's a catch. Sweet-Parker predicted reconnection would unfold at a glacial pace, far slower than what satellites and telescopes actually observe. If this model were entirely accurate, solar flares would take days to erupt, not seconds. Clearly, nature had other ideas. This glaring mismatch led to a breakthrough in the 1960s when physicist Harry Petchek proposed a radical alternative. Imagine those same magnetic fields not just squeezing plasma aside, but forming an X-shaped collision point. At the center of this X, the fields wouldn't just reconnect, they'd explosively rip apart, creating standing shock waves that funnel plasma outward at staggering speeds. Petchek's model finally explained why reconnection could release energy so quickly, matching observations of solar flares and magnetospheric explosions. But even this theory had gaps. While it worked beautifully for some conditions, it couldn't account for the chaotic turbulence seen in real-world plasmas, where magnetic fields twist into intricate, unstable knots. Today, the debate is far from settled. Modern researchers lean on hybrid models, blending elements of Sweet-Parker's steady squeezing with Petchek's explosive shocks. Supercomputer simulations reveal that reconnection isn't just one process, it's a cascade of micro-explosions, with tiny magnetic islands forming and merging in the chaos. These islands act like short-lived accelerators, slinging particles to near light speeds and solving part of the velocity puzzle, yet mysteries linger. For instance, why do some reconnection events like those in Earth's magnetosphere unfold symmetrically, while others, like solar flares, erupt with wild asymmetry? The biggest unresolved question centers on what triggers reconnection in the first place. Some theorists argue it's driven by plasma instabilities, tiny ripples that grow uncontrollably like waves breaking on a shore. Others point to external forces like the violent impact of a solar wind shockwave. Then there's the enigma of spontaneous reconnection, where seemingly stable magnetic fields suddenly rupture without any obvious trigger. It's as if space itself has hidden tripwires waiting to be nudged. Cutting-edge missions like NASA MMS are putting these theories to the test, flying through reconnection sites with instruments so precise they can track individual particles. Early data suggests reality is messier and more fascinating than any model predicted. Magnetic fields don't just snap cleanly, they fracture in fractal-like patterns with energy dissipating in ways that defy classical physics. Some researchers even speculate that quantum effects, normally negligible at cosmic scales, might play a role in these extreme environments. What's at stake isn't just academic. Accurate reconnection models could transform our ability to predict solar storms, design fusion reactors, or even probe the limits of Einstein's theories. Every flare, every aurora, every black hole jet is a cosmic experiment, one that's rewriting the rules of physics in real time. The theories we have are stepping stones, each one bringing us closer to deciphering the universe's most explosive handwriting. Black holes aren't just cosmic vacuum cleaners, they're some of the most powerful particle accelerators in the universe, and magnetic reconnection might be the secret behind their terrifying efficiency. Picture the edge of a supermassive black hole, where gravity twists spacetime into a vortex and magnetic fields wrap around it like a coiled spring. As matter spirals inward in the accretion disk, these fields stretch and tangle, building tension until, just like on the Sun, they snap and reconnect. But near a black hole, the stakes are infinitely higher. The energy released doesn't just create a flare, it gets funneled into narrow, ultra-fast jets shooting outward at nearly the speed of light, stretching thousands of light years across galaxies. These jets are among the most energetic phenomena in the cosmos, and reconnection could explain how they're launched. Simulations show that as black holes devour matter, their magnetic fields act like cosmic slingshots. When reconnection occurs near the event horizon, it flings charged particles along the black hole's spin axis, accelerating them to relativistic speeds. This isn't just theoretical. Telescopes like the Event Horizon Telescope have captured hints of twisted magnetic structures near black holes, while observations of distant quasars, bright galactic cores powered by black holes, show jet features that match reconnection-powered outbursts. Yet the scale is almost incomprehensible. A single black hole jet can carry enough energy to outshine its entire host galaxy for millions of years. In 2019, the Chandra X-ray Observatory spotted something extraordinary, a flare in the jet of the black hole at the heart of galaxy M87, with spectral fingerprints pointing directly to magnetic reconnection. The flare's timing and intensity suggested a sudden, violent release of stored magnetic energy, like a cosmic dam breaking. But here's where it gets stranger. Some theorists propose that reconnection near black holes might do more than power jets. It could help unravel how black holes lose energy over time. The Blandford-Zienagic process, a leading theory for jet formation, suggests that black holes can steal rotational energy from their own spin, converting it into magnetic power. Reconnection events might act as the release valves for this process, regulating how much energy gets channeled into jets versus heating the surrounding plasma. The implications ripple across the cosmos. These jets shape entire galaxies, heating interstellar gas and suppressing star formation. Without them, the universe might look radically different, denser, cooler, and clumpier. Even more intriguing is the possibility that reconnection near primordial black holes in the early universe could have seeded the first magnetic fields, setting the stage for everything that followed. So while we often think of black holes as dark, silent destroyers, they're also brilliant creators sculpting the cosmos with bursts of energy forged in the chaos of snapping magnetic fields. And every time a telescope catches a flicker in a distant jet, we're glimpsing a universal language written in arcs of plasma and fractures of space-time. Neutron stars take magnetic reconnection into the realm of the unimaginable. These ultra-dense stellar corpses, packing more mass than our Sun into a city-sized sphere, boast magnetic fields so powerful they could strip the electrons off atoms from 1,000 miles away. On their surfaces, magnetic forces aren't just strong, they're twisted into knots by the star's dizzying rotation, creating conditions ripe for the most violent reconnection events in the known universe. When these fields finally snap, they don't just release energy, they detonate it, unleashing bursts of X-rays and gamma rays visible across galaxies. Magnetas, a rare subclass of neutron stars, push this phenomenon to even more extreme levels. Imagine a magnetic field 1,000 trillion times stronger than Earth, so intense it warps the very structure of spacetime around the star. In 2004, astronomers witnessed what happens when such a field ruptures. A magneta named SGR 18020, 50,000 light-years away, produced a flare so bright it temporarily ionized Earth's upper atmosphere despite being halfway across the Milky Way. For a fraction of a second, the outpouring of energy rivaled the total output of our entire Sun for 100,000 years. And the culprit, a cataclysmic reconnection event in the star's magnetosphere, where pent-up magnetic stress violently realigned. What makes these outbursts so different from solar flares isn't just their scale, it's their underlying physics. On a neutron star, magnetic fields don't just thread through plasma, they're frozen into the star's solid, crystalline crust. When the crust fractures under immense magnetic pressure, it triggers starquakes, cosmic tremors that twist the overlying fields until they explosively reconnect. The aftermath resembles a cosmic lightning storm, with particle beams accelerated to near light speed and shockwaves rippling through surrounding space. Some theories suggest these events might even produce fleeting fireballs of electron-positron pairs, the same matter-antimatter annihilation seen in the early universe. Recent observations from telescopes like NASA NICER have revealed bizarre details about these processes. Some magneta flares start with a slow buildup, a weeks-long crescendo of smaller reconnection events before culminating in a final catastrophic snap. Others erupt without warning, suggesting hidden instabilities in the star's interior. Even more puzzling are the quasi-periodic oscillations detected in some X-ray bursts, flickering signals that hint at vibrating magnetic loops or whirlpool-like vortices in the reconnection zone. But the real mystery lies in what these events mean for the broader cosmos. Magneta flares might explain some of the most enigmatic signals we detect, like fast radio bursts, those millisecond-long blasts of radio waves whose origins have baffled astronomers for years. There's even speculation that certain gamma-ray bursts, once thought to come solely from supernova or colliding neutron stars, could be the death cries of hypermagnetized stellar remnants undergoing final apocalyptic reconnection. The deeper we look, the clearer it becomes. Neutron stars are nature's ultimate magnetic laboratories, where physics bends to extremes we can scarcely replicate on Earth. Each flare, each burst, is a message from the edge of possibility, written in the violent snapping of magnetic fields and the afterglow of spacetime itself. Some of the most energetic particles in the universe owe their existence to magnetic reconnection, a process so efficient at acceleration. It can launch subatomic particles to nearly the speed of light in the blink of an eye. Picture a cosmic pinball machine where charged particles like protons and electrons get trapped between collapsing magnetic fields. As those fields snap and reconnect, they create explosive shock waves that fling particles outward with unimaginable force. This isn't just theoretical. Earth-orbiting detectors have caught these ultra-fast particles, cosmic rays raining down from space, some carrying energies 1,000,000 times greater than anything produced in human-made particle colliders. Supernova remnants are among the most dramatic cosmic accelerators. When a massive star explodes, it sends a supersonic shockwave barreling through interstellar space, while tangled magnetic fields in its wake become prime territory for reconnection. As these fields break and reform, they transform the chaotic debris into a natural particle collider, boosting electrons to relativistic speeds. These accelerated particles then spiral along magnetic field lines, emitting synchrotron radiation, the eerie glow we see in images of supernova remnants like the Crab Nebula. Without reconnection, these celestial light shows wouldn't shine nearly as bright. active galactic nuclei take this process to even more extreme levels. At the cores of distant galaxies, supermassive black holes generate jets that stretch for hundreds of thousands of light years. Satellite observations reveal bright knots and flares along these jets, telltale signs of reconnection events acting like cosmic boost stations. Each time magnetic fields rupture in these regions, particles get an energy kick, creating bursts of gamma rays and X-rays detectable across the universe. Some researchers speculate that the highest energy cosmic rays, those with energies exceeding 100 billion electron volts, might originate in these violent, reconnection-powered environments. But the real mystery lies in the details. Laboratory experiments and simulations show that reconnection doesn't accelerate particles evenly. Instead, it favors certain energies, creating distinct bumps in cosmic ray spectra. This selectivity suggests hidden structures within the chaos, like microscopic turbulence or fractal-like magnetic geometries that act as particle filters. Even more puzzling is the role of plasmoids, those self-contained magnetic bubbles that form during reconnection. These fleeting structures might trap particles, bouncing them back and forth like balls in a cosmic lottery machine until they escape with tremendous energy. Understanding this process could rewrite part of astrophysics. For decades, scientists assumed shock waves were the primary cosmic accelerators. Now, evidence suggests reconnection might dominate in environments ranging from the solar wind to distant quasar jets. Some theories even propose that reconnection could solve the century-old mystery of ultra-high-energy cosmic rays, particles so powerful, their origins remain one of astrophysics' greatest puzzles. Every time a particle detector on Earth registers an extraordinary cosmic ray, it might be catching the aftermath of a magnetic field snapping somewhere in the void, a fleeting yet universal mechanism that turns the quiet hum of the cosmos into a symphony of high-energy sparks. What if our universe isn't alone but just one page in an infinite cosmic library where every possible version of reality exists simultaneously? This is the startling premise of the multiverse theory, a concept that stretches the boundaries of physics and philosophy alike. At its core lies the many worlds interpretation of quantum mechanics proposed in the 1950s by physicist Hugh Everett. Imagine every decision you make, every quantum-level event, not as a single outcome, but as a branching point where reality splits into parallel timelines. In one universe, you turned left today. In another, you turned right. The implications are staggering, a vast, ever-expanding web of alternate realities, each governed by the same fundamental laws but unfolding in wildly different ways. But the multiverse isn't just a quantum phenomenon. Cosmologists theorize that our entire universe might be one bubble in a frothy sea of inflating space-time. According to eternal inflation theory, the Big Bang wasn't a singular event, it was just one eruption in an endless cosmic foam, where new universes constantly bud off with their own unique physics. Some might have stronger gravity, others could harbor exotic particles we've never seen. In this view, the multiverse isn't just about alternate versions of Earth, it's about fundamentally different realities, each operating by their own rules. Now, here's where magnetic reconnection enters the picture. If these parallel worlds exist, could there be points where they inadvertently touch? Quantum physics suggests that empty space isn't truly empty. It's a seething quantum foam where tiny wormholes flicker in and out of existence. Under extreme conditions like those during magnetic reconnection, these fleeting portals might stretch wider, creating transient bridges between realities. Think of it like two soap bubbles momentarily merging before pulling apart. The energy released during reconnection events could theoretically warp space-time enough to pry open these microscopic gateways, even if just for a fraction of a second. The idea isn't pure speculation. Certain anomalies in cosmic ray data hint at particles arriving with energies that seem to defy known physics, almost as if they slipped through from a universe with different fundamental constants. Even more intriguing are laboratory experiments with quantum-entangled particles, which respond to each other's states instantaneously across vast distances. Could this spooky action at a distance, as Einstein called it, be a faint echo of deeper connections between parallel worlds? While mainstream science remains cautious, the tantalizing possibility lingers. Magnetic reconnection might not just be about energy release. It could be the universe's way of stitching together the fabric of reality itself. Every solar flare, every aurora, every black hole jet might leave behind traces of something far stranger, brief, shimmering cracks in the cosmic mirror, reflecting realities beyond our own. At the smallest scales of the universe, where the frenetic dance of particles defies classical physics, magnetic reconnection takes on a quantum dimension, one where the rules we know begin to blur. Picture a single electron caught in the turbulent whirlpool of a reconnection event. According to quantum mechanics, this particle isn't just a tiny dot moving predictably through space. It exists as a probability cloud, a smear of potential positions and energies. When magnetic fields violently snap and reconnect, these probabilities warp in ways even Einstein's relativity couldn't predict, creating conditions where particles seem to tunnel through barriers or vanish from one point only to reappear in another. Laboratory experiments with quantum plasmas, superheated gases where particles interact so rarely that quantum effects dominate, have revealed bizarre behaviors during reconnection. Electrons, instead of following smooth trajectories, suddenly jump across magnetic field lines as if teleporting, a phenomenon linked to the Heisenberg uncertainty principle. In simulations of neutron star magnetospheres, where magnetic fields are quadrillions of times stronger than Earth's, quantum fluctuations can momentarily create microscopic wormholes, transient bridges where particles briefly slip through what should be impassable magnetic barriers. These fleeting structures, lasting mere trillionths of a second, hint at a deeper connection between reconnection and the fabric of space-time itself. Theoretical models take this even further. Some physicists propose that under extreme conditions like those in the early universe or near black holes, quantum reconnection might twist space-time so violently that it momentarily opens portals to other dimensions. These wouldn't be the sci-fi gateways of popular imagination, but microscopic fractures where the fundamental constants of nature, like the strength of gravity or the mass of electrons, could differ slightly from our own reality. Such ideas remain speculative, but intriguingly, certain anomalies in cosmic ray data show particles with energy signatures that don't quite match known physics, as if they've slipped through from a universe with slightly tweaked rules. The key to unlocking these mysteries might lie in quantum entanglement, the strange phenomenon where particles remain instantaneously connected across vast distances. During reconnection, entangled pairs of particles could be violently separated, their quantum states imprinting information about the magnetic chaos onto distant detectors. Experiments with quantum sensors aboard satellites like China's Missions have already begun probing whether large-scale magnetic events like solar flares leave entangled footprints detectable across Earth's magnetosphere. While mainstream science remains cautious, the tantalizing thread connecting quantum physics, magnetic reconnection, and hidden dimensions grows harder to ignore. Every time a solar flare erupts or a black hole jet flickers, we might be witnessing not just an explosion of energy, but the universe's subtle way of testing the boundaries between realities, one quantum jump at a time. Wormholes have long been the stuff of science fiction, cosmic shortcuts threading through folded space, connecting distant points in the universe. But could these fantastical passages have roots in real physics? Enter Einstein-Rosen bridges, theoretical structures born from the equations of general relativity. These bridges are essentially tunnels through space-time, predicted to form when massive objects like black holes warp the fabric of reality so severely that two distant regions momentarily link. The catch: traditional wormholes collapse instantly, crushed by their own gravitational forces before anything could traverse them. This is where magnetic reconnection throws a fascinating wrench into the equation. During reconnection events, the sudden release of energy warps spacetime in ways eerily reminiscent of wormhole dynamics. Picture a solar flare's eruption. In mere seconds, magnetic fields snap and realign, unleashing energy equivalent to billions of nuclear bombs. That energy doesn't just dissipate, it distorts the surrounding spacetime, creating transient regions of extreme curvature. Some theorists suggest that under just the right conditions, say near a magnetar or during a black hole jet's formation, this distortion might briefly stabilize a wormhole's throat, counteracting the forces that would normally cause it to implode. The key lies in exotic matter, a hypothetical substance with negative energy density. According to wormhole models, such matter could prop open an Einstein-Rosen bridge long enough for traversal, acting as cosmic scaffolding against collapse. Intriguingly, the plasma turbulence generated during magnetic reconnection produces conditions where quantum effects mimic some properties of exotic matter. Lab experiments have observed particles behaving as if they carry negative effective mass in these chaotic environments, hinting at fleeting moments where nature might cheat the rules. Astrophysical observations add fuel to the speculation. Gamma-ray bursts, some of the most energetic events in the universe, often show signatures of magnetic reconnection coinciding with unexplained time delays in photon arrivals. Could these delays be evidence of light briefly taking a detour through a spacetime wrinkle? Even more provocative are anomalies in cosmic ray data, where particles appear with energies that suggest they traversed shorter distances than classical physics allows, as if they found a cosmic backdoor. Of course, mainstream science remains skeptical. Stabilizing a wormhole would require energies and control beyond anything observed naturally or even artificially. Yet the parallels between reconnection, spacetime warping, and wormhole mechanics are too tantalizing to ignore. Every time a solar flare erupts or a neutron star's crust quakes, we might be glimpsing the universe's workshop, where magnetic chaos toys with the very architecture of reality. Whether these phenomena truly open doors to other dimensions, or simply tease us with their almost but not quite resemblance, remains one of physics' most electrifying mysteries. The idea of time travel often feels confined to the pages of science fiction, but what if the universe holds natural mechanisms capable of bending time itself? Magnetic reconnection, with its explosive energy releases and spacetime warping effects, might be one such mechanism. At the heart of this possibility lies a concept from Einstein's theory of general relativity, closed time-like curves, or CTC. These hypothetical pathways through spacetime loop back on themselves, allowing an object or information to return to its own past. While CTCs remain theoretical, extreme environments like those during magnetic reconnection could provide the perfect conditions for them to emerge, however fleetingly. Consider the intense magnetic fields near neutron stars or black holes, where reconnection events unleash unfathomable energy. The sheer gravitational and electromagnetic forces at play don't just distort space, they twist the fabric of time. In these extreme regimes, simulations suggest that collapsing magnetic field lines could create temporary spacetime vortices, regions where time's arrow might curve into a loop. It's not quite a time machine, but rather a natural glitch, a momentary kink in reality where cause and effect could, in theory, tangle. But how would this work in practice? Imagine a magnetic reconnection event so powerful that it generates a gravitational wave strong enough to ripple through local spacetime. Under the right conditions, this ripple could intersect with itself, forming a closed loop, a CTC. Particles caught in this loop might experience time differently, cycling through the same moments repeatedly before the structure collapses. Lab experiments with plasma vortices have hinted at analogous behavior, where particles briefly enter self-sustaining loops of motion, echoing the theoretical time loops predicted near black holes. The sticking point is stability. Even if a CTC formed during reconnection, it would likely exist for only a fraction of a second before dissipating. Yet some physicists speculate that advanced civilizations, or future humans, might find ways to harness these fleeting phenomena, perhaps using directed energy to stabilize the loops long enough for practical use. Others argue that nature might already be doing this on a scale we haven't detected. Anomalies in cosmic ray data, for instance, include particles with energy signatures that seem to remember events they haven't encountered yet, almost as if they've slipped backward through time. Of course, mainstream science remains divided. Critics point out that CTCs violate causality, creating paradoxes that defy logical consistency. But proponents counter that quantum mechanics already allows for non-linear time effects at microscopic scales. Entangled particles, for example, communicate instantaneously across distances, a phenomenon some interpret as evidence of temporal flexibility. If magnetic reconnection can amplify these quantum quirks to macroscopic scales, even momentarily, the implications would rewrite our understanding of time itself. Whether these ideas ever move beyond theory hinges on our ability to probe deeper into the universe's most extreme environments. Every solar flare, every magnetar outburst, and every black hole jet might be hiding clues not just about how magnetic fields snap and reconnect, but about how time itself might fray at the edges under the right conditions. Until then, the tantalizing possibility remains. The universe's most violent magnetic explosions could be hiding keys to its greatest mystery, the nature of time. The cosmos is filled with phenomena that defy easy explanation, bursts of energy so intense they can outshine entire galaxies, yet so fleeting we barely catch them before they vanish. Fast radio bursts, or FRB, rank among the most perplexing. These millisecond-long pulses of radio waves arrive from deep space, packing as much energy as the sun emits in 80 years. Some repeat unpredictably, while others blast once and disappear forever. Although theories abound, from colliding neutron stars to alien signals, one possibility stands out: magnetic reconnection on an unimaginable scale. Imagine a magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth's, undergoing a catastrophic reconnection event. The resulting energy release could explain these brief, ultra-powerful signals, blasting across the cosmos like a lighthouse beam cutting through fog. Then there's gamma-ray bursts, the most violent explosions since the Big Bang. Lasting anywhere from milliseconds to minutes, these events flood space with high-energy photons, some traveling billions of light-years before reaching our telescopes. The collision of neutron stars or the collapse of massive stars into black holes are leading suspects, but reconnection might be the hidden engine behind their extreme brightness. When magnetic fields in a collapsing star's core twist and snap, they could funnel energy into narrow jets, accelerating particles to nearly the speed of light. Observations of Jabi afterglows often show signatures of turbulent magnetic fields, hinting that reconnection isn't just involved. It might be the spark that ignites the entire explosion. Even stranger are the anomalies that resist categorization. Take the Cow, an astronomical event detected in 2018, a sudden flare of blue light 10 times brighter than a typical supernova, fading within days. Or the bizarre Tasmanian Devil, a repeating explosion that defied models of stellar behavior. Both events left scientists scratching their heads. Could these too be the aftermath of extreme magnetic reconnection? The rapid energy release, the unpredictable recurrence, it all fits the profile of magnetic fields tearing apart and reforming under conditions we've yet to fully understand. What unites these mysteries is their sheer unpredictability. Unlike supernova or solar flares, which follow observable patterns, these events seem to emerge from nowhere, governed by physics operating at the edge of our knowledge. That's where Reconnection offers a tantalizing thread. Whether it's powering FRBs, shaping GRB jets, or triggering inexplicable flares, the process is a universal one occurring anywhere magnetic fields and plasma meet under extreme stress. Each unexplained burst might be a clue, a glimpse into the chaotic, high-energy dance of fields breaking and reforming across the universe. The deeper we look, the more these cosmic puzzles seem interconnected. Perhaps they're not anomalies at all, but signposts pointing toward a larger truth, that magnetic reconnection, in all its violent beauty, is the universe's way of sculpting its most spectacular phenomena. Every flash, every burst, is a message written in the language of collapsing fields and accelerating particles. And as we piece together their origins, we're not just solving astronomical riddles, we're decoding the hidden mechanics shaping the cosmos itself. Dark matter constitutes 85% of the universe's mass, yet it remains utterly invisible, an enigma that neither emits nor reflects light, detectable only through its gravitational tug on galaxies. But what if this mysterious substance interacts with magnetic fields in ways we've never considered? Most theories assume dark matter passes through ordinary matter like a ghost, unaffected by electromagnetic forces. Yet in regions where dark matter density spikes near black holes or in galactic cores, its gravitational influence could warp the fabric of space so severely that it twists nearby magnetic fields into unstable configurations. Picture a vat of dense, invisible syrup swirling through a maze of magnets. Though the syrup itself doesn't respond to magnetism, its sheer mass bends the magnet's field, straining them to the breaking point. Under extreme conditions, this indirect pressure might trigger reconnection events hidden from our telescopes, releasing bursts of energy we've yet to recognize. These hypothetical dark reconnections could explain puzzling cosmic phenomena. Take the perplexing gamma-ray excess at the Milky Way center, an unexplained glow that conventional astrophysics struggles to account for. While some attribute it to pulsars or particle collisions, another possibility lurks in the shadows: dark matter particles clumped in the galaxy's core, gravitationally twisting magnetic fields until they snap, producing sparks of high-energy radiation. Simulations of dense dark matter halos suggest that such interactions could generate subtle, repetitive flare signatures that might resemble noise until viewed through the right theoretical lens. Even more radical is the idea that dark matter's influence on reconnection could expose cracks in reality itself. Certain quantum gravity models propose that dark matter isn't just invisible, it's a bridge to a dark sector, a parallel universe with its own invisible particles and forces. In this shadow realm, magnetic fields might behave differently, coupling with dark matter in ways that sporadically erupt into our visible universe during reconnection. Imagine a candle flickering behind a curtain. The light you see isn't the flame itself, but its distorted glow. Similarly, what we perceive as a solar flare or magnetar burst might sometimes be the echo of a far stranger event unfolding in the dark sector. The key to testing these ideas lies in subtle anomalies. Some astrophysicists hunt for reconnection events with unusual energy signatures, bursts that release too much power too quickly, or particles with trajectories that defy known physics. Others analyze the distribution of fast radio bursts, searching for patterns that align with predicted dark matter structures. Even lab experiments like CERN Large Hadron Collider are probing whether certain high-energy collisions could produce transient dark sector particles that briefly stretch magnetic fields before vanishing. While the evidence remains speculative, the implications are staggering. If dark matter does influence reconnection, it would rewrite our understanding of both cosmic magnetism and the invisible scaffolding of the universe. Every unexplained flare, every anomalous particle detection might be a breadcrumb leading us toward a deeper truth. one where the boundaries between visible and invisible, between our universe and others, are far more porous than we ever imagined. String theory suggests that the fundamental building blocks of the universe aren't particles, but tiny, vibrating strands of energy filaments so small, a single atom would dwarf them like a planet dwarfs a grain of sand. These strings don't just wiggle randomly. Their vibrations determine the properties of everything we know, from electrons to galaxies. But here's where it gets mind-bending. String theory requires extra dimensions, 7 more than the 4 we experience, curled up so tightly they're invisible to us. What if magnetic reconnection, with its explosive energy releases, momentarily tugs at these hidden dimensions, making them detectable? Imagine a magnetic field not as a simple line of force, but as a higher dimensional string vibrating through multiple layers of reality. Under normal conditions, we only perceive its 4-dimensional shadow, the part that interacts with our familiar space-time. But during reconnection, when fields rupture and reconfigure, the violent energy surge might briefly excite these strings into states that reveal their full multidimensional nature. It's like plucking a guitar string hard enough that it momentarily vibrates in harmonies usually too faint to hear. Some theorists propose that certain anomalies in reconnection events, unexplained particle energies or fleeting distortions in spacetime, could be signatures of these higher dimensional vibrations poking through. Laboratory experiments add tantalizing hints. In particle colliders, scientists have observed energy discrepancies during high-energy collisions, tiny, missing amounts that don't match predictions. While most attribute this to known particles, a fringe hypothesis suggests it might be energy leaking into extra dimensions. Similarly, during extreme reconnection in astrophysical plasmas, the sheer energy density could warp localized spacetime enough to uncurl a hidden dimension, allowing strings to vibrate in ways that imprint bizarre effects on surrounding matter. Picture a whirlpool forming in water. As the vortex intensifies, it briefly pulls deeper layers to the surface. In the same way, reconnection's turbulence might expose dimensions usually locked away. The most speculative and thrilling implication ties this to wormholes. If strings can vibrate across higher dimensions, could reconnection events create transient bridges between them? Some string theory models suggest that certain string configurations, called Dirichlet branes or D-branes, could act as gateways when perturbed by immense energy. During a solar flare or magnetar outburst, the chaotic magnetic snap might nudge nearby D-branes into alignment, opening a microscopic passage. These wouldn't be traversable tunnels, but their gravitational or quantum signatures could linger, perhaps explaining why some cosmic rays arrive with energies that seem to defy conventional physics. Of course, critics argue that without direct evidence, these ideas remain mathematical fantasies. But proponents counter that the universe's most violent phenomena are precisely where we should expect hidden physics to surface. Every time a black hole's jet flickers or a neutron star's crust quakes, we might be witnessing not just magnetic chaos, but the faint reverberations of strings dancing through dimensions beyond our own. Whether string theory's extra dimensions exist remains one of science's great unanswered questions. But if they do, magnetic reconnection could be the cosmic magnifying glass that brings them into focus, one explosive snap at a time. Supercomputers have become our cosmic laboratories, allowing us to simulate magnetic reconnection under conditions so extreme they dwarf anything in the observable universe. Take the early moments after the Big Bang, when space was a seething ocean of plasma and primordial magnetic fields. Advanced simulations reveal that reconnection in this environment didn't just happen. It exploded in fractal-like cascades, with each snap of the magnetic fields triggering dozens more in an unstoppable chain reaction. These digital recreations show filaments of energy weaving through the infant cosmos, shaping the large-scale structure of the universe itself. The sheer violence of these events suggests they may have left behind gravitational ripples still detectable today, echoes of the universe's first magnetic screams. But the simulations grow even stranger when applied to hypothetical cosmic strings, defects in space-time left over from the early universe, thinner than an atom yet stretching across galaxies. Models suggest that if a cosmic string passed through a region of strong magnetic fields, the resulting reconnection would be unlike anything seen in nature. The string's immense tension would warp space-time around it, twisting magnetic field lines into helical coils before they violently snap. The energy release wouldn't just produce light or heat, it might vibrate the cosmic string itself, sending gravitational waves pulsing through the cosmos at frequencies no detector has ever spotted. What's truly mind-bending are the hints of multidimensional effects buried in these simulations. When researchers incorporate higher dimensions from string theory into their models, reconnection takes on bizarre new behaviors. Magnetic fields no longer simply break and reform, they momentarily knot through hidden dimensions, creating transient structures that resemble quantum-scale wormholes. One simulation from the University of Tokyo showed particles briefly gaining energy from nowhere, as if siphoned from an unseen dimension. Another revealed strange interference patterns in the plasma, like shadows cast by forces operating beyond our three-dimensional perception. These digital experiments aren't just academic exercises. They're helping scientists interpret real cosmic mysteries, like the inexplicable cold spots in the cosmic microwave background or the occasional detection of ultra-high-energy particles with no obvious source. If magnetic reconnection in extreme environments can bridge dimensions or shake cosmic strings, it might explain these enigmas as side effects of a deeper, hidden physics. The challenge lies in testing these ideas. While supercomputers can simulate scenarios no telescope will ever see, the real universe has a way of surprising even our most advanced models. That's why teams at facilities like the Large Hadron Collider are now probing whether high-energy collisions might produce miniature reconnection events with telltale signatures of extra dimensions. Meanwhile, gravitational wave observatories scan the skies for any ripple that matches the unique frequency a cosmic string reconnection would produce. Every time these simulations run, they push the boundaries of what we thought possible, revealing a universe far stranger and more interconnected than we imagined. Magnetic reconnection, it seems, isn't just a local phenomenon, it's a universal thread woven through every scale of existence, from the birth of the cosmos to the hidden dimensions that might lurk just beyond our perception. Pilots and astronauts have long reported encounters with phenomena that defy conventional explanations: strange lights, magnetic anomalies, even moments where time itself seemed to distort. One of the most compelling cases comes from declassified military reports, like the infamous 2004 Nimitz incident. U.S. Navy pilots tracking an unidentified object off the coast of California described their radar systems malfunctioning as the craft executed maneuvers no known aircraft could replicate. But the most chilling detail, the pilots reported their instruments registering extreme magnetic fluctuations, as if their jets had flown through an invisible storm of warped fields. Similar accounts echo through decades of aviation history. Astronauts aboard the International Space Station have logged anomalies during solar storms, not just radiation spikes, but brief, localized distortions where compass needles spun wildly before settling. The common thread in these reports: sudden, unexplained disruptions to magnetic instruments, precisely what you'd expect near a violent reconnection event. But here's where it gets speculative. Could some of these anomalies be accidental brushes with transient portals, where snapping magnetic fields briefly opened a crack in spacetime? Take the 1991 case of a Soviet cosmonaut who, during a routine spacewalk, radioed back in panic about a ripple in the darkness ahead of him. His suit's magnetometer spiked off the charts before the phenomenon vanished. Decades later, declassified documents revealed ground stations had simultaneously detected a magnetic surge in that exact orbital region, one that matched no known solar or terrestrial activity. Then there's the baffling account from a retired Air Force pilot who, while flying a reconnaissance mission near the Arctic Circle in the 1980s, described entering a bank of eerily glowing fog. His jet's navigation systems failed entirely, and for nearly 12 minutes his altimeter insisted he was both climbing and descending simultaneously. When he emerged, his clock was mysteriously behind those on the ground. While skeptics dismissed it as instrumentation failure, researchers studying magnetic reconnection note that extreme field collapses can theoretically warp local spacetime enough to affect timekeeping, a phenomenon predicted in certain quantum gravity models. The most haunting question isn't whether these events happened. The records confirm they did, but what they represent. Are these mere technological glitches, or could they be glimpses of something far stranger? Laboratory experiments with plasma vortices have shown that under the right conditions, magnetic reconnection can produce self-contained energy loops resembling theoretical wormholes. If nature replicates this on a cosmic scale, even fleetingly, it might explain why so many eyewitness accounts describe sensations of missing time or distorted perception during magnetic anomalies. Whether these incidents point to hidden physics or simply the limits of our current understanding, they underscore a tantalizing possibility. The universe's most explosive magnetic phenomena might occasionally tear the veil between our reality and others. Every unexplained radar blip, every pilot's baffled report, could be a breadcrumb leading us toward a truth far wilder than fiction. And as we push further into the cosmos, we may find that the greatest mysteries aren't just out there, they're woven into the very fabric of the forces we're only beginning to understand. Long before telescopes or satellites, ancient cultures looked to the skies and saw not just stars but doorways. The Norse spoke of Bifrost, a shimmering rainbow bridge connecting our world to Asgard, home of the gods. Aboriginal traditions described sky ropes or dreaming tracks, celestial pathways where ancestors traveled between realms. These myths share something startling. They don't depict static stars but dynamic, luminous structures, bridges that appear and vanish, often amid storms or celestial disturbances. Could these stories be more than fantasy? Could they be humanity's earliest records of magnetic reconnection events? Consider the descriptions. Bifrost wasn't just a metaphor. Norse texts describe it as a burning bridge, unstable and flickering, guarded by a god who ensures only the worthy may pass. Compare that to satellite footage of a solar flare, an arch of plasma writhing in the sun's atmosphere, collapsing and reforming in minutes. The parallels don't stop there. The Aboriginal sky ropes were said to hum with energy, visible only during specific celestial alignments, eerily reminiscent of auroras, where ionized particles spiral down magnetic field lines, creating rippling curtains of light. Even the timing fits. Many of these myths emerged during periods of heightened solar activity, when auroras and plasma storms would have been visible far beyond their usual polar confines. Then there's the Dogon people of Mali, whose millennia-old cosmology included detailed knowledge of Sirius, a star invisible to the naked eye from their latitude. They described it as part of a celestial hinge, a gateway where energies converged. Modern astronomy reveals Sirius is part of a binary system with intense magnetic interactions, exactly the environment where violent reconnection could occur. Coincidence, or could oral traditions have preserved eyewitness accounts of cosmic phenomena that science is only now decoding? The most tantalizing clues come from ancient art. Petroglyphs in the American Southwest depict spiral-shaped figures beside what scholars interpret as star portals. Similar symbols appear in Celtic carvings and Mesopotamian cylinder seals, often accompanied by zigzagging lines resembling plasma filaments. Laboratory experiments show that when magnetic fields reconnect in plasma, they form helical structures, spirals within spirals that glow with an ethereal light. To an ancient observer, might these fleeting structures have looked like doorways to another world? Skeptics argue these connections are retroactive, that humans simply projected myths onto random celestial events. Yet the consistency across cultures separated by continents and millennia is hard to dismiss. From the Vedic Agni's path to the Maya's world tree, these myths share uncanny details, bridges that appear in crisis, demand passage rituals, and vanish abruptly. Just as reconnection events flare unpredictably, channel energy along specific magnetic pathways, and dissipate before stabilizing. Perhaps the ancients weren't just storytellers, perhaps they were the first astrophysicists interpreting cosmic violence through the lens of their beliefs. Every time a solar storm painted the sky with otherworldly light, they might have witnessed something far stranger: the universe's magnetic seams straining, twisting, and briefly parting. Whether these myths were literal descriptions or symbolic interpretations, they point to a profound truth. The boundary between myth and reality might be as thin as the transient gates formed when magnetic fields snap and cosmic doors swing open, if only for an instant. Modern science is no longer content to simply theorize about cosmic mysteries. Teams around the world are actively probing the boundaries of reality, hunting for evidence that magnetic reconnection might unlock more than just energy. Take DARPA groundbreaking quantum augmentation program, an initiative exploring whether controlled electromagnetic pulses could manipulate spacetime itself. While the program's official documents speak in cautious terms about emerging physics, insider accounts hint at something far bolder: attempts to recreate on a microscale the conditions of extreme reconnection seen in magnetars or black hole jets. The idea: if nature uses snapping magnetic fields to warp spacetime, perhaps we can engineer our own versions, not just to study them but to harness them. Across the Atlantic, CERN Large Hadron Collider isn't just smashing particles, it's hunting for fingerprints of extra dimensions. When protons collide at nearly light speed, their accompanying magnetic fields twist and rupture in miniature reconnection events. Some theorists suggest that if hidden dimensions exist, these fleeting moments of magnetic chaos might stretch the fabric of reality enough to reveal them. In 2018, detectors recorded anomalous energy losses during certain collisions, gaps that matched predictions of energy leaking into higher dimensions. While the findings remain controversial, they've ignited fierce debate about whether reconnection could be the universe's backdoor to realms beyond our perception. Even more audacious are private ventures like Breakthrough Starshot, which aims to propel nanoprobes to nearby stars using laser-powered light sails. Hidden in their technical specs lies a lesser-known ambition: to test whether concentrated magnetic pulses could stabilize microscopic wormholes long enough to transmit data. The concept borrows from reconnection physics, imagining carefully timed magnetic snaps as a way to stitch spacetime temporarily. It's speculative, but not science fiction. NASA's Innovative Advanced Concepts program has funded similar research, exploring how plasma vortices in magnetic fields might mimic the spacetime curvature needed for shortcuts across the cosmos. What ties these experiments together is a quiet revolution in how we view reconnection. No longer just a cosmic curiosity, it's becoming a toolkit, a way to test the universe's most extreme possibilities in labs and colliders. Every time a solar flare reminds us of nature's raw power, or a black hole's jet defies expectations, we're glimpsing phenomena that might one day be more than observed. They could be engineered. The line between discovery and invention has never been thinner or more electrifying. The prospect of magnetic reconnection opening gateways to other realms isn't just a scientific curiosity, it's a philosophical lightning rod. Imagine a future where we could harness these cosmic portals for interstellar travel, reducing journeys that take millennia to mere moments. The implications would dwarf every technological leap in human history, reshaping our place in the cosmos overnight. But with such power comes profound ethical dilemmas. What happens if a stabilized gateway destabilizes, unleashing energies or entities we can't control? The same phenomenon that might connect us to distant stars could also rip open unintended breaches, like a surgical tool turning scalpel to wrecking ball in the wrong hands. Consider the risks of space-time itself becoming compromised. Theoretical models suggest that artificial wormholes, even microscopic ones, require exotic matter with negative energy to stay open. If reconnection-based gateways demand similar conditions, miscalculations could trigger catastrophic feedback loops. Picture a cascading collapse where one unstable portal's collapse triggers others, fraying the fabric of local spacetime like a zipper unraveling. The consequences range from gravitational anomalies to time dilation pockets, regions where clocks tick at wildly different rates. Even without doomsday scenarios, the mere act of bridging realities raises unsettling questions. Would transit between worlds introduce invasive physical laws? A universe where gravity operates slightly stronger could crush unwary travelers. One where fundamental constants differ might dissolve matter entirely. Then there's the Pandora's box of unintended contact. If gateways exist, could they be two-way? Historic precedents like the introduction of invasive species on Earth where harmless stowaways devastated ecosystems hint at the chaos of unregulated cross-reality exchange. More chillingly, what if something on the other side notices our experiments? The search for extraterrestrial intelligence has long operated under protocols to avoid attracting hostile attention, but prying open dimensional doors could bypass those safeguards entirely. Ethical frameworks struggle to keep pace. Traditional space law, like the Outer Space Treaty, bans celestial territorial claims but says nothing about manipulating spacetime itself. Philosophers argue whether creating gateways constitutes an act of hubris akin to Prometheus stealing fire, or a moral imperative akin to curing disease. Some compare it to nuclear fission, a discovery that could power civilizations or destroy them depending on governance. Yet unlike atomic energy, reconnection tech might not offer a clear off switch. Once a gateway forms, closing it could require energies rivaling its creation, leaving pioneers trapped in their own ambitions. Amid these uncertainties, one truth emerges: the line between breakthrough and peril is razor thin. Every leap toward understanding magnetic reconnection brings us closer to capabilities once relegated to myth. Whether we use them wisely or at all may depend not just on our ingenuity, but on our humility to recognize that some doors once opened can't be shut. The next decade promises to revolutionize our understanding of magnetic reconnection, with spacecraft venturing further and probing deeper than ever before. The European Space Agency's Thor mission, slated for launch in 2027, will dive into Earth's turbulent magnetosphere with unprecedented precision. Armed with sensors 100 times more sensitive than previous instruments, Thor won't just observe reconnection, it'll dissect it, tracing individual particles as they whip through collapsing magnetic fields at nearly the speed of light. But the real intrigue lies in its secondary objective: hunting for anomalies in energy distribution that could hint at quantum-scale spacetime warping. Some theorists suggest that if reconnection briefly opens microscopic wormholes, Thor detectors might catch the aftermath particles with bizarre trajectories or energies that defy conventional physics. Meanwhile, NASA Interstellar Probe aims to push beyond the heliosphere, venturing where no dedicated mission has gone before, into the interstellar medium where the Sun's magnetic influence wanes. Scheduled for the mid-2030s, this bold mission could encounter regions where cosmic magnetic fields tangle freely, untouched by stellar winds. Here, reconnection might unfold in its purest form, offering clues about how the process operates near exotic objects like neutron stars or black holes. Engineers have even speculated that the probe's instruments might detect something stranger: fluctuations in the interstellar magnetic field that align with predictions of higher dimensional physics. If hidden dimensions influence reconnection, their signatures could magnify in the quiet vastness between stars. Not to be outdone, Japan's upcoming Ares 2 spacecraft will target ultra-fast reconnection events in Earth's magnetotail, the cosmic equivalent of capturing lightning in a bottle. These sudden, violent snaps occur faster than theory predicts, and Array's 2's ultra-high-speed cameras aim to catch them in action, the mission's secret weapon. Quantum sensors capable of measuring minuscule spacetime distortions. While designed to study plasma turbulence, these sensors might accidentally pick up something far more profound: ripples in spacetime itself during extreme reconnection, potentially revealing whether these events briefly warp the fabric of reality. The most tantalizing possibilities lie with proposed missions like NASA's Star-X, which would study reconnection near supermassive black holes. Imagine a telescope tuned to the X-rays generated when magnetic fields snap just outside an event horizon, an environment where gravity twists spacetime so severely that reconnection could momentarily puncture it. Simulations suggest these events might leave echoes in the radiation spectrum, subtle fingerprints of quantum entanglement between our universe and something else. While Star-X remains in early planning stages, its potential findings could blur the line between astrophysics and metaphysics. What unites these missions is their potential to transform reconnection from a cosmic curiosity into a tool, one that might let us probe the universe's most guarded secrets. Every time a spacecraft captures a magnetic field snapping in the void, we're not just collecting data. We're testing the boundaries of reality itself, searching for cracks where the impossible might slip through. Science gives us the framework to understand magnetic reconnection, the equations, the observations, the lab experiments. But just beyond the edges of what we can prove lies a playground of possibility, where solid facts blur into tantalizing speculation. Take the well-documented energy releases during reconnection events. We know they warp spacetime locally, bending light and altering particle paths in measurable ways. That's established physics, yet when you scale those distortions up to the extremes near neutron stars or black holes, the math suggests something stranger: brief moments where spacetime curvature could become so severe it folds back on itself. Could that create a traversable bridge? The equations allow for it, but nature hasn't yet handed us observable proof. This dance between the known and the theoretical isn't just academic, it's how breakthroughs happen. Consider how Einstein's general relativity was once dismissed as abstract speculation until eclipses and orbiting stars confirmed its predictions. Today, we're piecing together similar clues about reconnection's wilder implications. Satellite data shows particles occasionally emerging from flares with energies that skirt the edges of plausibility, as if they've been boosted by mechanisms we haven't fully modeled. Simulations suggest these could be signatures of quantum effects or higher dimensional leakage, but skeptics rightly counter that unusual doesn't mean impossible within known physics. The line between not yet explained and revolutionary discovery is often razor-thin. What makes this frontier so electrifying is how it challenges our assumptions. For decades, we thought of reconnection as a messy but ultimately local event, a cosmic short circuit. Now, theories like quantum entanglement in plasma or holographic universe models hint that these magnetic snaps might encode information in ways that ripple across spacetime. Imagine a solar flare not just as an explosion, but as a message written in the language of twisted fields and accelerated particles, one that might only make sense if we're missing a key piece of the puzzle. Of course, speculation needs guardrails. For every compelling "what if," there's a risk of sliding into pseudoscience. That's why researchers stress the distinction between testable hypotheses, like the idea that reconnection could generate detectable gravitational waves, and untestable conjectures about interdimensional travel. The difference: one can be falsified by experiments, the other remains in the realm of thought experiments. Yet history shows that today's thought experiments sometimes become tomorrow's textbooks. The trick is balancing open-minded curiosity with rigorous skepticism, a tightrope walk that's produced everything from quantum mechanics to the discovery of black holes. So where does that leave us? With more questions than answers, and that's exactly as it should be. Every unexplained particle detection, every anomalous energy spike in a lab plasma is an invitation to look deeper. Maybe the wilder ideas about cosmic gateways will fizzle under scrutiny, or maybe, just maybe, we're on the verge of realizing that magnetic reconnection isn't just a process in our universe, but a tool the universe uses to weave itself together across dimensions we're only beginning to imagine. Either way, the journey to find out promises to be as thrilling as the destination. From the flickering auroras over Earth's poles to the cataclysmic flares tearing through distant galaxies, we've traced magnetic reconnections, invisible fingerprints across the cosmos. What began as a puzzle in plasma physics has unfolded into something far grander, a phenomenon that shapes stars, fuels black holes, and might even weave hidden threads through the fabric of reality itself. We've seen how these violent snaps of magnetic energy defy classical laws, accelerate particles to unfathomable speeds, and warp space-time in ways that flirt with the impossible. Laboratories recreate miniature versions, spacecraft capture their aftermath, and theorists dare to imagine their wildest implications, from cosmic particle accelerators to fleeting portals between worlds. Yet for every answer, new mysteries emerge. Why does reconnection happen so explosively? What secrets hide in the quantum whirlpools of collapsing fields? Could those brief moments of magnetic chaos truly be cosmic gateways, stitching together realms beyond our perception? The line between established science and thrilling speculation has never felt thinner or more electrifying. We stand at the edge of a frontier where the universe's most mundane forces, magnetism, plasma, gravity, converge in ways that challenge everything we think we know. So here's the question that lingers, whispered by every solar flare and echoing in the hum of distant magnetars. If magnetic reconnection can bend the rules of space-time, even momentarily, what else might it bend? Could the universe's vast magnetic tapestry, woven through every star and galaxy, hide doors to worlds beyond our own? The evidence isn't conclusive, but the possibility alone rewrites how we see the cosmos. Not as a static stage, but as a dynamic, shimmering web where energy, space, and perhaps even realities intersect in unseen ways. Now it's your turn. Where do you think this cosmic detective story leads next? Could those fleeting bursts of magnetic energy be more than meets the eye, or are we glimpsing shadows of something even stranger? Drop your wildest theories below, and if you're hungry for more mysteries at the edge of science, hit subscribe. The universe's greatest secrets are still waiting, and the next breakthrough might be just one magnetic snap.